In this lesson we're going to look at catalysts and the effect that catalysts have on the rate of reaction. We're going to begin with the definition for a catalyst. So catalysts are substances that we use to increase the rate of reaction. Okay, so a substance that increases rate of reaction. But we also need to specify how it does that. And this is one of the only things that we change that affect rate that doesn't either increase the frequency of those collisions or the energy of those collisions. So when you add a catalyst to a reaction, you are leaving the same frequency of collisions and the energy of those collisions does not change. But what a catalyst does is lower the activation energy. That means that more of those collisions that were already occurring but didn't have enough energy, well, now they do. It's no different if you take a metaphor. You're queuing up to ride a roller coaster at Thorpe Park, and the height requirement is 2 meters. Let's say something crazy like that. So the height requirement is 2 meters, and the vast majority of people will not be able to ride that roller coaster. However, if the height requirements were lowered to 1 meter, then basically everybody will be able to ride that roller coaster. Now, has anybody in that queue suddenly gotten taller? No. All that's changed is the requirements for a successful collision. Okay, so remember, the activation energy is the amount of energy that the reactant particles must collide with in order to have a successful collision and therefore become products. If you lower that energy requirement, that activation energy, then more collisions will be successful and therefore the rate of the reaction will increase. So a catalyst is a substance that increases rate of reaction by lowering the activation energy. Now, you don't need to know any specifics about how that occurs. All you need to know is that it does happen. And what happens is that the catalyst creates an alternative pathway. So you're starting with your reactants and you end with your products. But what the catalyst does is create an alternative pathway in order to get from reactants to products, and the energy of that pathway is lower, so less energy is required to get from reactants to products, therefore more of those collisions are successful. The other thing you need to know about a catalyst is it is not used up in the reaction. So if I added 5 grams of a catalyst to a reaction, I would get all 5 grams of it back at the end. It is not used up in the reaction. So a substance that increases rate of reaction by lowering activation energy and will add in and is not used up in the reaction. So if we think of some sort of everyday uses of catalysts, a catalytic converter on your car, turning carbon monoxide into carbon dioxide and nitrogen oxides into nitrogen, a really important piece of kit to lower the harmful emissions from engine exhaust. And the main element in that catalytic converter is platinum, which is a very, very expensive metal. Now, we can offset that cost by the fact that it doesn't get used up. The amount of platinum in that catalytic converter the day it rolls off of the production line, and the amount of platinum in that catalytic converter when you've had it for 18 years, much like my car, there's still the same amount of platinum in there. So it doesn't get used up. So yes, it is an expensive element, expensive metal, but because it doesn't get used up, it lasts a very, very long time and you can recover it. So why do we use catalysts? Well, obviously we want to speed up rates of some reactions. That makes sense. You get more of your product quicker. That's an obvious incentive. Another thing about using catalysts is if we think about the other methods for increasing rate, increasing the pressure, increasing the temperature, well, these things are expensive. It's very expensive to run a high pressure reaction because you've got to maintain that pressure, and that has quite a high cost. High temperatures, again, very, very difficult to maintain those high temperatures. It's very, very expensive. Whereas using a catalyst allows you to speed up the rate of reaction without having to have that reaction at such a high temperature and high pressure. So it actually, in the long run, even though some of these catalysts are quite expensive in the first place, it allows you to lower the temperature and pressure of the reaction, which saves you money. Because yes, that catalyst is expensive, but you can get all of it back and use it again. So they're really useful in industry for lowering the cost of industrial chemical processes. So what we're going to look at is how some catalysts affect a reaction. We're going to look at a very simple reaction. So I've drawn a reaction profile diagram, which is exactly what we would have seen in topic 5 when we were talking about the energy of reactions. And if we just remember, we have our reactants on the left, our products on the right. The fact that the products are lower in energy than my reactants tells us this is an exothermic reaction. But that's not what we're interested with at the moment. So what we're looking at here is this bit here, the activation energy. And if we remember, that is the amount of energy the reactants need to collide with in order to produce products. So we demonstrate that with a curve here, okay, because not all the reactants have that amount of energy yet. Some of them do, some of them don't. And when they collide, they need to have this amount of energy in order to react. And by adding a catalyst, all we are doing, we are not changing the energy of the reactants, we are not changing the energy of the products, we are not changing the frequency of collisions. All we are doing is lowering that activation energy. So when you have a catalyst, you simply lower the activation energy. So if I just draw it there. So it starts and ends in the exact same place. That's really important. Starts and ends at the exact same place because the energy of the reactants and the energy of the products has not changed. However, our activation energy is now lower. So if I draw a new arrow up to there, this is our activation energy with a catalyst, okay, which is lower than the activation energy of the original reaction, so the rate of that reaction will increase. Another way of looking at that is with a distribution curve like this. So what we have on the x-axis is energy, okay, low energy, high energy. And then on the y-axis, how many particles have that amount of energy. So in a reaction, not all the particles have the same amount of energy. Some of them have low energy, some of them have high energy, some of them have sort of average energies. So this curve shows the distribution of energy within our particles. So most of them have this amount of energy, okay, sort of an average amount of energy. Some of them have very, very high energy, some of them have very, very low energy. And this line here represents the amount of energy needed for a successful collision and for a reaction to occur. And that is the activation energy. So every single one of these particles here, when they collide, they don't react. Every one of these particles on this side of the activation energy, when they collide, they just bounce off each other. They have unsuccessful collisions. However, these ones here, these particles have enough energy because they are above the activation energy. So when these particles collide, they have successful collisions, they become products. So let's say that this is, roughly speaking, I don't know, 15% of all the particles. So only 15% of the particles, when they collide, they actually react. So when we add a catalyst, what changes? Well, when we add a catalyst, we lower the activation energy. If the activation energy is lower, then we're also going to get these particles that are going to collide and have successful collisions. And now we're much closer to 30-40% of our particles having enough energy to collide, which is going to increase our rate of reaction. Now, at no point did I change the energy of the particles, and I didn't change the frequency of the collisions either. I simply, by adding a catalyst, have lowered the activation energy, so now more of those collisions that were happening anyway are going to be successful because more of them will be above the new activation energy, which has been lowered by the presence of the catalyst. So this experiment that we're going to look at is very, very simple. It's very, very similar setup to the ones we've looked at before. So we're going to have a conical flask with a delivery tube going into a measuring cylinder. Now the actual reaction is the decomposition of hydrogen peroxide. So hydrogen peroxide, some of you might be familiar with, is the active ingredient in hair dye. So hydrogen peroxide is H2O2, and it's a very, very unstable molecule, and at room temperature it breaks down into water and oxygen. And if we balance it, I'm going to get that. So that's the reaction. So if I had some hydrogen peroxide in that conical flask, it would be breaking down into water and oxygen, and that oxygen will travel through the delivery tube and be collected in our measuring cylinder. Now again, we could substitute this for a gas syringe. That would work just as well. So our hydrogen peroxide is breaking down into water and oxygen, and we're going to collect the oxygen over time. We'll be able to measure the rate of that reaction. Now it's quite a slow reaction. If you were looking at it, you wouldn't really see any bubbles, and you'd be waiting a very long time before you got any significant amount of oxygen in that measuring cylinder. However, if you add a catalyst which speeds this reaction up by lowering the activation energy, suddenly the amount of oxygen being produced increases. So what we are going to do is look at this reaction, adding a variety of different catalysts, and measure how much oxygen is being produced over time for each catalyst. And then you'll be able to compare the rate of reaction for each catalyst, and you'll be able to see for all of them that they will increase the rate from no catalyst, and we'll be able to look at which catalysts actually increase the rate more than others, because some catalysts are better suited to different reactions. So for example, I spoke about the catalytic converter. Platinum is really, really good at converting carbon monoxide into carbon dioxide and nitrogen oxides into nitrogen, so we use platinum as our main catalyst. If we were talking about the industrial production of ammonia in the Haber process, well, actually iron is a really good catalyst for that process. So not all catalysts have the same effect. Some have a greater catalytic effect on certain reactions. So we choose that catalyst for that purpose. So we're going to look at a variety of different catalysts, and by comparing the rate of production of oxygen, we can actually then look at the effect each one of those catalysts has on the rate of the reaction. So here we have the setup from the experiment. So we have our conical flask with our hydrogen peroxide. We have our inverted measuring cylinder filled with water in a trough of water. Again, you could replace this whole apparatus with a gas syringe. That would work just as well. And then we have our delivery tube going to the measuring cylinder attached to a bung, which we're going to stick in the top of our conical flask to collect the oxygen that's being produced. So just to recap, we've got hydrogen peroxide, which is a very unstable compound, and it's breaking down into water and oxygen gas, which we can collect. So if we look at it now quickly, you can barely see any signs of a reaction. Now it is happening, okay? And when we have hydrogen peroxide, we have to store it in these special containers with a depressurized lid, because it's producing oxygen the whole time. If it had a normal lid that's sealed completely, the oxygen would build up and eventually the bottle would explode. So you need to have a special lid on the bottle so that it can allow that oxygen to escape when it builds up. Also, we keep all of the hydrogen peroxide in the fridge, again, which makes sense if we think about rates of reaction. Rate of reaction slows at lower temperatures because less particles have less kinetic energy, so they are less frequently colliding, and also less of them having successful collisions. So we can stop it from breaking down by cooling it down. So just here at room temperature, very little appears to be happening. Now I'm just going to demonstrate the method. I'm not going to go through the whole experiment. I'm not going to repeat it for different catalysts, and we can go through some results afterwards. So I've got my hydrogen peroxide, everything else is set up, and if we look at the method, it just says to add your catalyst, replace the bung, and then measure the volume of oxygen collected after 100 seconds, I believe it says. So after 1 minute, sorry. So we're going to set that up, we're going to do that, and then what you would then do is repeat that using different catalysts, and you'd be able to compare the amount of oxygen collected in a minute. And the catalyst that obviously produces the most in a minute is the best catalyst, and the one that produces the least is the worst catalyst. But you should see that all of the catalysts produce more than would have been produced if we'd just left the hydrogen peroxide to decompose on its own. So all of them are going to have a catalytic effect, but some of them are going to have a greater effect than others. So get a spatula of our catalyst. Now I'm using potassium iodide. Get a reasonable amount on there, there we go. I'm just going to pop that in, replace the bung, and then hold that underneath our measuring cylinder. Just give it a bit of a swirl. And you can see bubbles of gas are being produced, and that gas is going to be oxygen, because remember, that's the reaction, hydrogen peroxide breaking down into water and oxygen. Okay? So if we look at the color of our solution, it has changed this sort of yellow color. That's just because of the iodine from the potassium iodide. Okay, if you get it in aqueous solution, you get this sort of orangey color. And you can see now we're getting quite a rapid production of oxygen, which we weren't getting before. So the hydrogen peroxide was breaking down before, just very, very, very slowly, not enough that you could observe any of that oxygen being produced. And all I've done is add a catalyst. And at the end of this experiment, what I would be able to do is, if I were to filter it, I would be able to recover all of that catalyst that I added. Okay, remember the catalyst is not used up in the reaction. We've got 9 more seconds. There you go, now we can stop collecting. And then if we have a look, we can see that we collected 32 centimeters cubed of oxygen in a minute. So we could, if I don't think this is one of the catalysts that's in the results table, but that's what we would record, and then we would rinse everything out, reset, so we need to refill this measuring cylinder, and would repeat the experiment using different catalysts, but importantly keeping certain things the same. It's important to have control variables, so I'd make sure I use the exact same concentration of hydrogen peroxide, the exact same volume of hydrogen peroxide, that I use the exact same mass of my catalyst. There's no point comparing different catalysts if you're using different amounts of those catalysts each time. Other things that could be different, so this is a potassium iodide, which is a white powder. So if one of my other catalysts perhaps had a higher surface area or a lower surface area, again, that wouldn't be a fair test. So I need to make sure that the surface area of my catalyst, again, is comparable. Now what I've got here is a classic chemistry demonstration called elephant's toothpaste. And it's the exact same principle as the experiment we were looking at before. It's hydrogen peroxide decomposing to break down into water and oxygen. Now, the only difference really from the experiment I showed you before is I've used much more concentrated hydrogen peroxide here. Okay? Now you can see some bubbles there, so you can see that this is already breaking down to produce oxygen. Now, I'm not really interested in measuring the oxygen here because I'm not trying to compare the catalyst. I'm just trying to show very clearly the effect a catalyst can have. So what I've added is, so I've got more concentrated hydrogen peroxide and I've added a little bit of washing up liquid. And all that does is that the oxygen that's going to be produced, instead of just making, being bubbles of gas, is going to create bubbles in the washing up liquid. And we'll get sort of foam being produced. Now, I've also done it in a volumetric flask, again, because what we want to do is try and funnel that foam that's going to be produced into a narrow area, and then it should come out of the top almost like toothpaste, hence the name elephant's toothpaste. Now, if you scale up this experiment, you can get really huge foam that comes out the top of this. Now, in the past, I've had this where it's come out the top and hit the ceiling. This one is not going to be that dramatic because this is a new lab with a nice new white ceiling. But if you are interested in seeing this on a large scale, then look on YouTube for David Dobrik, Elephant's Toothpaste. I believe he, very irresponsibly I might add, did a huge scale version of this experiment, and you'll just see just how much oxygen is produced when they added the catalyst to that hydrogen peroxide. So again, just to recap, I've got my hydrogen peroxide in there with a little bit of washing up liquid, and this is much more concentrated than what you would have been using or than what I used in that previous experiment. And I'm just going to add a catalyst, and you'll be able to see very clearly that as soon as I add that catalyst, the effect we're going to have on the rate of the reaction. Here it goes. Hence the name Elephant's Toothpaste. You can see the way it's all flying out the end of that volumetric flask, almost like toothpaste. Now, you might have seen this demonstration before or online, and if you put food colouring in it, then obviously you get different colours of the foam. But all this foam this is just the washing up liquid, foam from the washing up liquid being produced because of the rapid production of oxygen from the breakdown of the hydrogen peroxide. This slight sort of yellow colouring is just because the catalyst I used was potassium iodide, so again we're getting a little bit of aqueous iodine being produced. And I'm not sure if you can really see it, but there's quite a lot of steam coming off of this. Okay, it's a very, very exothermic process, so it's very, very hot. But all we are really looking at is these bubbles here are just oxygen that's been produced from the decomposition of the hydrogen peroxide, and all we've done is add a catalyst to make that oxygen be produced at a much, much faster rate. I mean, you were looking at it before I added the catalyst, you could see a few bubbles, and it's undeniable that the rate of this reaction is massively increased by adding that catalyst, and that's simply because the catalyst lowers the activation energy, so more successful collisions occur. So here we have some example results of what we would have seen if we'd been able to carry out this experiment. So exact same method as what was shown previously, and then we would just repeat that method using different catalysts. So we'd measure the volume of oxygen produced after 1 minute with diced potato, and then wash it all out, measure out a fresh batch of hydrogen peroxide, and repeat the experiment to see how much oxygen was produced after 1 minute with manganese oxide. So these are the results from our different catalysts. So we would use potato, manganese oxide, copper oxide, iron oxide, and some liver. Okay, this isn't a typo. We really are going to use potato and liver. So the first question is, hydrogen peroxide decomposes to produce oxygen gas. Write an equation for this reaction. So it doesn't specify whether this needs to be a symbol or a word equation, so we're going to write both. So hydrogen peroxide decomposes to produce oxygen gas, so hydrogen peroxide produces water and, oops, should have been a plus really. Don't know why I wrote and. And the symbol equation for that is hydrogen peroxide, H2O2 goes to H2O and O2. In order to balance that, you need 2 of those and 2 of those. So which of the substances you added to the hydrogen peroxide made the most effective catalyst for this reaction? So really we've got 2 we could choose from, can't we? So we've got the manganese oxide and the diced liver. Okay, these are both the most effective catalyst. Because they produce the most amount of oxygen after 1 minute. Now actually it's a little bit misleading. They didn't get to 100 centimeters cubed and then stop. What's happened is that was the size of the measuring cylinder we were using. So if you wanted to see the difference between the manganese oxide and the diced liver, what you would need to do is have a larger measuring cylinder so that you could actually compare, because all that's happened is in a minute they've both completely filled the measuring cylinder. Or you could time which one filled the measuring cylinder first, so which one was the quickest to produce 100 centimeters cubed, and then you could perhaps compare them. And we can also see that from this, the diced potato was the least effective catalyst. So which substance would you add have the most effective catalyst? So either manganese oxide or diced liver. Both of them. From our experiment, we can't tell the difference between the two. Which of these substances did not appear to have a catalytic effect? Well, they all did, so none. But I will add, however, diced potato had the least catalytic effect. So describe how catalysts speed up reactions. Okay, they lower activation energy via an alternative pathway. So they basically just offer an alternative way to get from reactants to products that has a lower activation energy. So that increases number of successful collisions. Okay, it doesn't change the number of collisions. Same number of collisions are occurring, it's just now more of them will be successful. What is the difference between the catalyst present in liver and that in manganese oxide? So again, we're going to come back to the liver. Now, those of you that are good at biology should know that the liver contains a large amount of enzymes. Okay, and enzymes are an example of a biological catalyst. So liver contains enzymes. Okay, and enzymes are a biological catalyst. And if we think about biological catalysts for a minute, when we were talking about catalysts before and how they're quite expensive, certainly if we're using precious metals as catalysts, well, biological catalysts have a large number of advantages. Number one, they're completely renewable. Usually if they're enzymes, they can be produced by bacteria. So you have a bacteria that produces the enzyme that you want. You can produce and reproduce that bacteria on large scales and then essentially break open the bacteria using a centrifuge to obtain that enzyme that you were after. And then you could just grow more bacteria and therefore get more enzymes. So it's completely renewable. And also another thing that's really good about biological catalysts, and especially if we think about some examples of biological catalysts, usually in detergents, if you buy washing powder, you can get bio and non-bio washing powders. And the good thing about biological catalysts is that they operate at much, much lower temperatures. If you think about the operating temperature for most enzymes, it's approximately 37 degrees, which is a really quite, in terms of industrial chemistry, is a very, very low temperature. So if you could have a catalyst which works really effectively at low temperatures and is completely renewable, then that is a massive advantage. Finally, we're going to look at this tree map, which is going to give us an overview of everything we've spoken about so far in terms of collision theory. Okay, so we're going to talk just an overview of temperature, concentration, pressure, surface area, and catalyst. How do they affect rate of reaction, and how do we explain that in terms of collision theory? And just to reiterate, collision theory states that reactant particles must collide with enough energy to react. And that amount of energy is referred to as the activation energy. and any of those collisions that do have enough energy are successful collisions, and all of the collisions that don't have that amount of energy are unsuccessful collisions. So we'll start with temperature. If we increase temperature, so I'm going to increase for all of these. So increasing temperature gives particles more kinetic energy, so they have more frequent collisions because they're moving around more and with more energy, so they're more likely to collide with each other. They're going to have higher energy collisions because they've got more energy. Therefore, rate of reaction increases. Okay, that's simple. So increasing temperature gives particles more kinetic energy. They're moving around more, so they're more frequently colliding. Also, when they do collide, they've got more energy, so the rate of reaction increases. Let's look at concentration. So increasing concentration increases number of particles in a fixed volume. You must talk about volume when we're talking about concentration. Volume is really important. So increasing number of particles in a fixed volume, meaning more frequent collisions. Therefore, rate of reaction increases. Now, temperature affects almost any reaction. Concentration only really applies when we're dealing with aqueous solution. So if we have an aqueous reactant, then concentration is applicable. Pressure only applies if we have a gas. So if one of our reactants is a gas, then pressure is applicable. And again, it's the exact same explanation as concentration. If we increase the pressure, I'm using the wrong pen, so increasing pressure increases the number of particles in a fixed volume. So it's the exact same definition as for concentration, but for concentration we're dealing with aqueous solutions, but pressure we're dealing with gases. But both of them, if you increase them, they increase the number of particles in a fixed volume, so you get more frequent collisions. Therefore, rate of reaction increases. Okay, now surface area. Now when we're dealing with surface area, we are talking about solids. We need a solid reactant. So, increasing surface area increases the number of surface particles. Because remember, if you've got a solid, only the particles on the surface of that solid can react. So if you've got more surface particles, you've got more frequent collisions. Therefore, you have a higher rate of reaction. And finally, what we've been talking about, catalysts. Okay, so adding a catalyst lowers activation energy by providing an alternative pathway, so an alternative way of getting from reactants to products. Therefore, more successful collisions. So notice how in all the others we've talked about more frequent collisions, but here we're talking about more successful collisions because the number of collisions does not change, it's just more of them are successful now. Therefore, rate of reaction increases. Okay, so that summary there will allow you to answer any collision theory question, whether you are changing the temperature, the concentration, the pressure, the surface area of the catalyst. These are the things that are going to be worth marks. Okay, and obviously just remember that if you're doing the opposite, if you're decreasing temperature, it gives particles less kinetic energy, less frequent collisions, lower energy of collisions, therefore rate would decrease. Okay, so remember the opposite of this for all of these is always true. So just make sure that you are confident that if you are asked to describe why rate of reaction slows down at a lower concentration, that you are able to, in terms of collision theory, explain that process.